Okay, so in this lecture video, we will talk about second derivatives. So recall that when you have a scalar function, we can get its gradient. And if we have a vector function, we can get its divergence as well as its curl. So for instance, you have the gradient. The gradient of a scalar function is a vector. So we can, since it is a vector quantity, we can get its divergence as well as its curl. So we have the divergence of a gradient, which can be written as this. And we also have the curl of a gradient, which can be written as this one. Now the divergence of a vector function is a scalar. So since it is a scalar, we can only get its gradient. So we have the gradient of the divergence, which can be written as this one. Okay, and then we have the curl of a vector function. We know that it is a vector. So we can get its divergence and also its curl. So the divergence of a curl can be written as this. And then the curl of a curl can be written as this one. Now let us investigate each one of these species. So let us start with the divergence of a gradient. So the divergence of a gradient, we can rewrite it as this one. So this is actually the del operator in component form. And then we dot it with the gradient of f, which we have obtained in the previous discussion. So we have the gradient of f in component form. Okay, now since this is a dot product, then we can only, or we will only multiply the like components. So say for example, you have this one, the partial derivative with respect to x. So this is the x component of your del operator. And then we have the x component of the gradient of f. So multiplying this, we will get the second partial derivative of f with respect to x squared. Okay? And then do the same for the other components, the y and the z components. So as you can see, um, the divergence of a gradient is a scalar function, which we have here a second derivative of f with respect to x squared, second derivative of f with respect to y squared, plus the second derivative of f with respect to z squared. Or we can rewrite it as this one. So we can actually take out this multiplied by the scalar function, and then this one is actually the square of the del operator, or yeah, so you have here the second partial derivative with respect to x squared plus second partial derivative with respect to y squared plus the partial second derivative of with respect to z squared multiplied by f, or operating on f. So we have del squared f, and it is called, or we can call this the Laplacian of the scalar function f. Okay, now we can also have the Laplacian of a vector. So say for example, you have a vector function v. Now the Laplacian of a vector function v, so it can be expressed as this one. Now take note that this is the Laplacian of a scalar. So v sub x here is a scalar, which is the x component of your vector function v. So you have del squared v sub x, x hat, plus del squared v sub y, y hat, plus del squared v sub z, z hat. Okay? So this is the Laplacian of a vector. And then for the second one, so again, the divergence of a gradient leads us to the Laplacian. Okay, so for the second one, you have to take note of this. The curl of a gradient is always equal to 0. Okay, the curl of a gradient is always equal to 0. And then for the third one, we have the gradient of the divergence. Now take note that this is rarely used in physical application. So this notation is not usually used or useful. It's not useful in physical applications. And then for the fourth one, we have the divergence of a curl. And take note that this is always equal to 0. The divergence of a curl is always equal to 0. And then for the last one, we have the curl of a curl, which when we apply the backup rule, we will get this one. Okay. Now take note that this notation here is just the same as this, number 3. And then this one, we have the Laplacian of a vector. Okay, so therefore, there are only two kinds of second derivative. So the first one is this, and then the second one is this one, the Laplacian of a vector. Okay, so the Laplacian, and then we have here the gradient of the divergence. Okay, so let's have some examples. You have calculate the Laplacian of the following. So the first one is a scalar function t sub a, which is equal to x squared plus 2xy plus 3z plus 4. So we have to get the Laplacian of this function. So we just have to rewrite it this way. Okay, so we have the second partial derivative of t sub a with respect to x squared plus the second partial derivative of t sub a with respect to y squared plus the second partial derivative of t sub a with respect to z squared. Now this is your vector function. This is your scalar function. First is we have to get the first derivative, and then usbo na po siya na derive para makuha na to ang second derivative. Okay, so this is your t sub a, and then first is we have to get the first derivative of this function with respect to x. So since we are dealing with partial derivative, this means that we will treat the others as constants. So for example, you have this one. Differentiating this with respect to x, we have 2x plus 2y plus 0 plus 0. So you have 2x plus 2y. And then again, we will differentiate this with respect to y. So we will get 0 plus, so we have here 2x plus 0 plus 4. So you have here only 2x. And then differentiating this scalar function with respect to z, we have here 0, 0, and then we have 3, then we have 0. So we only have 3 here. And then we will repeat the differentiation process since it is second derivative. Okay, differentiating this one with respect to x, so you will get 2 plus 0 or just 2. Then this one, differentiating this with respect to y, you will get 0. Differentiating this with respect to z, you will get also 0. So we have here the Laplacian of our scalar function t sub a is equal to 2. Okay, now let us have this one. Let us get the Laplacian of this scalar function, which is equal to sine x, sine y, sine z. So again, we can rewrite it in this way. So it is quite long. And then start differentiating or getting the first derivative. Okay, so in getting the first derivative, first partial derivative, we will just treat the other terms as constant. So say for example, we are differentiating with respect to x, so we will treat sine y and sine z as constant. So we just have to copy it. Sine y multiplied by sine z times the derivative of sine x. So we will only multiply this one, sine x. We'll only derive sine x. So the derivative of sine x is cosine x. Okay? And then uh, with respect to y, you have sine x, copy sine z, and then differentiate sine y. So you have cosine y. You have sine x, sine z multiplied by cosine y. And then with respect to z, so copy sine x, copy sine y, and then differentiate sine z. So its derivative is cosine z. So you have sine x, sine z, sine x multiplied by sine y multiplied by cosine z. And then proceed with the second partial derivative. Okay, so from here, uh, from this, no? So we will get the second partial derivative or the derivative of this with respect to x. So again, we will only differentiate those with x. So copy this one, sine y, sine z. The derivative of cosine x is negative sine x. So you have here negative sine x multiplied by sine y multiplied by sine z. And then differentiating along the y. So you have copy sine x, copy sine z, and then the derivative of cosine y is negative sine y. So you have negative sine x, sine y, sine z. And then lastly, you have the third term, which is this one. You just have to copy sine x, sine y, and then differentiate cosine z. So you have negative sine z. So you have here negative sine x, sine y, and sine z. Now notice that these are just the same. So you can add these three terms here. So you will get negative 3 sine x, sine y, sine z. So you have here the Laplacian of the scalar function t sub b is equal to negative 3 sine x, sine y, sine z. Okay, now for the last one, we have a vector function v, which is equal to x squared x hat plus 3x z squared y hat minus 2x z hat. Now, the Laplacian of this vector function can be expressed as this. Okay, so take note that this notation here, del squared, can be written as this one. Okay, so you have this vector operator. You have this operator. It is not a vector operator, but it is an operator operating on v sub x. So this is the x component. The y component of your Laplacian is this. So you have your del squared here operating on v sub y. And then the third component or the z component, so you have the del squared operator operating on v sub z. Okay, so we just identify v sub x, v sub y, and v sub z. So v sub x is x squared, v sub y is this one, 3x z squared, and then v sub z is 2x z. So let us then get the second partial derivatives of this. Okay, so we start with the x component. So you have the second partial derivative of x squared with respect to x. So its first partial derivative with respect to x is 2x, and differentiating this again, we will get 2. And then here, if we operate this on x squared, we will get 0. We will get 0 also. Okay, So you have 2x hat. And then this one, operating this on b sub y, which is equal to 3x z squared, you have 3z squared, the first partial derivative. And then differentiating this again, we will have 0 na. Kaya wala na may x na nabilin. And then this one, operating this on 3x squared, we will get 0 since differentiating with respect to y, walay y diri ah. So we can treat this as constant. And the derivative of a constant is equal to 0. And then for this, we will get 6xz for the first partial derivative. And then differentiating it again, we will get 6x. Okay, so I hope you have followed through the discussion. So you have 6xy hat. And then here, first partial derivative with respect to x. So you have negative 2z. Second partial derivative, since wala na may x, this will become 0. This is operating or differentiating with respect to y. That would give us 0. And then differentiating with respect to z, this will give us negative 2x. But the second derivative will give us 0 since wala na may z. Okay, so you have the Laplacian of the vector function v is equal to 2x hat plus 6xy hat. Alright. Okay, so for your assignment, you have to prove that the divergence of a curl is always 0, and you can check it for this vector function v sub a equal to x squared x hat plus 3xc squared y hat minus 2xc z hat. Okay, so another video is coming up.